Time to start the final session of today. And the next speaker is Adrian Constantin from the University of Vienna. And he's going to talk about solutions of the Euler equation on the rotating sphere. Please.
Thank you very much. It's a pleasure being here. And my talk is about stratospheric flow and modeled as an Euler equation on a rotating sphere. So I will try first, this is joint work with Pierre Germain, who at the time when we did this was at the Courant Institute, now he moved to Imperial College. And I will try first to motivate what we are investigating physically and then present the main ideas of our results. So if you look at the planets of the solar system, you have the gas giants, these four, then there is Earth, and you have the solid planets. Now from the, what you see here in these typical figures, photographs, is this is the top of the troposphere. So the troposphere is where the clouds are, and then above it is the stratosphere. So, the problem with the planets that are not gases is there is no, in many of them, there is no stratosphere. So I want the stratosphere because, like the name says, in the stratosphere, things are stratified. And because they are stratified, you can think of the atmosphere like an onion. So it's rotating, but it's two-dimensional. So that helps. There is a change of density in the vertical, but it's a fundamental help to simplify matters. And the other thing that you observe here is that, well, there are some differences, namely in Jupiter there is the big red spot here, and Saturn has a hexagon at near the North Pole, and there are other. But basically the main flow is zonal, which means it's basically, there are these bands here, it's basically east-west. And there are perturbations, like these vortices that appear, but and the colors have to do with the composition of the gas that is there. So, right, so what I would like, what we wanted to look at is how to, well, taking the Euler equation in this context, because the other advantage of the stratosphere is that it's inviscid flow. So you don't have to deal with the Navier-Stokes equations, you can deal with the Euler equation in a rotating system. Right, so these are the coordinates that I'm going to use. So theta is going to be latitude, phi is longitude, and I'm going to normalize the radius to be 1, and the planet is rotating around the polar axis with the velocity that depends on, I mean, it's not important how big that is, but it changes. There is a problem with the, I mean, there is the Harry-Bohr theorem. You cannot find, you need the minimal atlas for the sphere has 2 charts. Okay, so you cannot have just one. There is a singularity, but this is not a problem because, in a sense, what you can do is, so in blue, this is one chart. You eliminate. This is this is called the international date line, not the real one, because the real one is not a half circle because of boundaries between countries. So it's including the North Pole. You take this out, then you have a chart, and then you rotate, and you take this part here out. So this is this transformation here. So basically, with suitable rotations, you have one chart, and then you rotate, and you have a second one. So even if there are singularities in the equations, you just change the chart. So the singularities are only by choice of the chart and are not relevant. So you have, okay, they have a tangent bundle. It cannot be globally parallelized because this Harry-Bohr theorem. So we take these kind of vectors, okay? These are the tangent vectors. This is the volume element. And we have gradient, divergence, and the Laplace-Beltrami operator that look like take this particular form on the sphere. Okay, so these are just standard definitions in spherical coordinates. I don't want, I mean, a lot of the geophysical literature consists in approximations, like F-plane approximation would say that if the distances that you consider are not too large, then what you can take the tangent plane and think of your flow. I mean, basically consider your projection on this, and do as if it were flat geometry. And there is another extension called beta plane, where when you do this expansion of the curvature, you go one further term, not just at the next order, and then you have another term, beta plane. The reason why I don't want to do F-plane or beta plane, so flat geometry, is that we would like to look at global flows, and doing them on a sphere or on this, it's quite different. In particular, on the sphere, there are a lot of symmetries that are there because, and they are very important. So, okay, the Laplace-Beltrami, this is the scalar product. And the important thing is to consider the spherical harmonics. So these are the eigen functions of the eigenvalues of the Laplace-Beltrami operator. And they are denoted, one typical notation is yjm. So the eigenvalues are we take average 0, okay? So that means 0 will not be an eigenvalue for us because because of this constraint, the eigenfunction should be 0, so it's not there. Okay, so the first the eigenvalues are minus j times j plus 1, where j is an integer, different. Now integer means different things I think in France 0 is an integer, okay, in Germany no, it's a special thing, or at least in Austria, okay, 0 is natural number plus 0. So this is j is greater or equal 1, and the eigenspace has dimension 2j plus 1, and it's for, I mean, you can write them down, it's a polynomial, and then some of them are zonal, most are not. One is zonal, the others are not, but they have, so these are important. So now the governing equations. These are the Euler equations. So two-dimensional Euler equation on a sphere. The fact that you are on a sphere, you can see here in the cosines and sines and things of the latitude. U and U0 and V0 are the, U0 is the east-west, V0 is north-south velocity, roughly. Omega is the rotation of the planet, positive. Rho 0 is a density that will depend only on Z. You have no Z derivatives here because we solve it at every layer and then try to match them together. This is the third component of because the vertical velocity is 10 to the 5 times smaller than the horizontal one. So it's really negligible in the stratosphere. So vertical velocity is 0. This means that this component of the three-dimensional Euler equations just becomes this. And this is mass conservation. Okay? Now there is the temperature is related to the density in this way. Okay? This is the equation of state. But basically when we solve this, so the point of view that we take, rho 0 we know, it's a function of Z. Then we determine the corresponding pressure, and then if we know the pressure, you can find the temperature. Okay? And if you need to know. Now, because this is two-dimensional, you have a stream function in spherical coordinates that looks like this. Yeah, so the stream function comes from here. And when you eliminate the pressure from these two equations, what you find is this vorticity equation in spherical coordinates. And right, so the next thing that we want to do, stationary solutions of this thing lead to traveling wave solutions. Okay, so basically, what we will try to solve this this elliptic equation, okay, where delta is the Laplace-Beltrami equation, and if we find a solution of this, then this is how you can accommodate it to a three-dimensional solution, so that is time-dependent. So this is traveling wave here, and this is the z-dependence to stack them on top of the other, and this is the associated pressure, and you can write the formula for the temperature also if you want to. Now, okay, so this is, like I said, some singularities are, because, I mean, this thing here, if you look at the definition of this meridional velocity, there is a cosine of theta, and that will become 0 at the poles, but also at the poles, the circles of latitude become smaller, so then if you combine these two things, this is not singular. Okay. I'm only going to talk about regular solutions, so not weak solutions. Everything is, all the derivatives and all the PDE should hold in the classical sense. Okay, so it doesn't have to be C infinity, but okay, and now this is, okay, so this is the Euler equation in a frame rotating at speed omega about the polar axis, and this is, you can write it in terms of the stream function like this, and you see this is where I mean, in the expression of the Laplacian, and here the cosine, and here these are the signs that this is in spherical coordinates. So now, if you know, it's much easier to deal with the stream function, yes. And actually, you can you have when you have, this is the equation with omega, means that the sphere is rotating, and okay, these are the covariant derivatives, and there is a complex structure defined by this thing. So the equations are, and if you look for the vorticity, you can write the Euler equation in this form. This is the material derivative. Because you are on the sphere, you need you have the Biot-Savart law to recover from the vorticity the stream function by means of this integral. The green function looks like this. This is the distance. It satisfies the standard thing with this is the delta distribution at some point, and then the Gauss this factor here is to enforce the Gauss constraint. Okay, so these are standard things, and still the equation. So there is a symplectic structure. This is the Poisson bracket, and you can write this vorticity equation in Hamiltonian form like this. And there are some conservation laws that will be very important regarding well-posedness. So the Biele-Kato-Maida thing can be adapted to this setting. I mean, this is known that it works. So you have global well-posedness in HS for S bigger than 2. So the issue of existence of solutions is not a problem. What we are interested in is some special solutions that are physically relevant and the question of stability. So, okay, so first of all, there are some invariants that one can use. This one here, okay, the omega stands for the rotation, the 0 is if it's not rotating. So if you solve on a non-rotating sphere and you try to move your results to the sphere, it works, but you have to pay a price. It's surprisingly delicate, but this is how this, so if this solves the one on the sphere, this solves the one on the rotating, this on the fixed one. There is a scaling invariance that works this way, and there are the group of O3 acts. Okay, the action is defined in this way, and the solutions are invariant under rotations. Okay, so this is something that can be is useful. The integrals of motion that are known are kinetic energy. U is the velocity field, U and V. This Casimir, so-called because of the Hamiltonian structure. So any function of this, integrated over the whole sphere will be an invariant. And the other thing is that the first eigenspace of the Laplace-Beltrami operator, so if I take, these are the coefficients when I expand it, and so we define these coefficients in this way. This is the standard scalar product. And what happens is that this thing here is preserved. So in particular, when omega is 0, this is 1, so you have 3 invariants. When you have rotation, it's just the one with m equals 0 that is invariant, but the others, if you want, for the others, it's the absolute value that is invariant, okay, from here. So already at the level of invariance, there is a subtle influence of the rotation. Okay, so we look for stationary solutions, so no time dependence. This is what the vorticity equation becomes. And now you can look at this as, you can interpret this geometrically, the gradient of the string function and of the potential vorticity. This should be vorticity, and because of rotation, you add this thing that's called then potential vorticity. These are parallel, okay? And basically, if at near any point where the gradient, where there is no stagnation, you can deduce this one here. But so if something if a solution of this would be a solution of that. Locally, if the gradient is different of this is also true, but they are not equivalent. So, for example, psi equal a constant. The interesting thing here, any zonal solution. So zonal is something that depends only on latitude. Okay, so will solve this, but obviously not necessarily this one. So, for example, psi equal 1 doesn't solve this. Okay, for f equals 0, but it solves that. So this is not equivalent, but it is. And there are some non-explicit solutions. So first of all, zonal solutions. So functions that depend only on theta. Theta is latitude. Any function of this type will be a solution. And the other class of explicit solutions are built on these spherical harmonics, and they are called Rossby-Haurwitz waves. So basically, the spherical harmonics have 2 indices. Okay, but one doesn't matter. This is just an eigenfunction. J is minus j times j plus 1 is the eigenvalue. And if you take this function here to be linear, then the fact that then it translates to these things. And these Rossby-Haurwitz waves, so they could be zonal when this eigenfunction is zonal. And when this is not zonal, they are not zonal. So these are large waves that are observed in the atmosphere, and it's the stability of these things that we are interested in. And from this, you can construct solutions, traveling wave solutions by the thing that I've been saying. Now, I'm going to discuss 2 results. One result is a rigidity result, telling you that if you have a classical solution of this for some omega is the rotation, if you have the freedom to choose f because of the structure of the vorticity equation, if f prime is positive, then the solution has to be constant. The surprising thing is f prime is bigger than -6, then it's a zonal flow modular rotation. Now, this is a standard thing if this would be the first eigenvalue. I mean, for me, the first eigenvalue is, but it's not the first, it's the second. And this is because of the symmetries of the sphere. So, for an arbitrary manifold, there is a recent paper co-authored by Pierre Constantin, okay, where this kind of result is proved for the first eigenvalue. This is the second, -6 is the second eigenvalue. And this is possible, so the result for the first eigenvalue would correspond to this, f prime bigger than -2. Here it's -6 because the way to prove this is you have to, I mean, you play around with inequalities, so you multiply with psi, you integrate, you derive some inequalities, and then something has to be 0. And the invariance you fix. So it's just playing around, but this is the result, and it is optimal because we have at -6 we have a Rossby-Haurwitz wave that shows that you cannot do better. Okay? So this is a rigidity result. I don't present the proof because it's just clever multiplications with something and integration by parts. So there is right. So now what you can use this for is you can use this invariance to start with a solution. Okay, so there are a few solutions that were of this. I'm talking about this elliptic thing here. So there are 4 special choices of f. There are some solutions available. And there is this trick for a fixed sphere to pass to the rotating sphere, and there is also this possibility to use the symmetry to have modulo or rotation. So what you can do, for example, this is a solution that is a zonal solution, okay, for this f. And then what you can do, because you have this rotational invariance, from this you build this, and this is not anymore zonal. Okay, there is a dependence on latitude here, but it's obtained from a zonal one by rotation, and it looks like this. So the same trick you can do here. This is another zonal solution for this complicated f. And then when you combine with the rotation, you can get this expression, and it looks, these are the levels of the streamline. Okay? And I can place this point wherever I want. So you get a few solutions of this type. Right. So now what we want to, the question that I want to address next is the stability. And there is a very powerful method, so nonlinear stability, this is what I want. So nonlinear stability in the sense that if you start close, you will stay close for all times. And there is an approach that Abel developed by consisting in, if you take invariance, okay, this is kinetic energy, this is this, and you take invariance, you build yourself a functional in the hope that you can make the first, so you have to choose this such that the first variation gives you the Euler equation, I mean the equation of interest, and then the second variation everything has the same sign, and then you can conclude stability. So this is, as general methods go, this is the best you can try for. So in this setting, we take a zonal flow of this type. Okay, so little f. So this is the stream function. It depends only on theta. This corresponds to this velocity field that is zonal, so there is no meridional flow. And this would be the vorticity. And if I can find an A such that, so f, and this is g, okay, this expression here is g. So if I can fulfill this, then this functional Arnold type will have a second variation of this thing, and this is exactly what is missing to make this strictly bigger than 0, and therefore you get a bound by a kind of Taylor expansion argument. So this is what, and the interesting thing is that this method, so it's a small, I mean, things like this exist in the literature. In particular, there's a paper by Taylor that goes a few years back where he uses this. What we did in this theorem, it's an incremental improvement of these things, but the nice thing is that in particular, it applies to the blue giants, okay, to Uranus and Neptune. I go back to them to notice something helpful if you believe that, okay, so these are basically in red here are the zonal flows. This is how the zonal velocity, the major velocity looks like this. And what you notice is that in these problems have, when there is an inflection point, you cannot make that inequality work. And if you look at the flows on Neptune and Uranus, they have fewer oscillations than Saturn and Jupiter. So if there is a chance for this Arnold method to work, it would be likely here rather than here. And this is indeed the case. Also, the flow here is it's much faster, but it changes. You see here you have, all of these flows go in both directions, but it's much more complicated on Jupiter and Saturn. So I go back now to this Arnold implementation of this Arnold idea. And basically what we do, this is a prototype for the flow on, so what we get when you compute this, for this flow, you get this expression. This is a polynomial of degree 2 in cosine square. You have a ratio in order to, so you can manage, and what the zonal flow on both things is stable. You can choose a constant. There is a choice of a constant there that I can choose to alter and I can choose the constant accordingly to prove that both zonal flow patterns are stable. Unfortunately, this doesn't work for Jupiter and Saturn. Well, it's not a big difference, but it doesn't work. It's impossible to make it work. And right. So this result of Arnold is about zonal solutions. Okay, but it can be, what happens if you allow yourself to have a phi dependence also on longitude? Well, you can try a similar thing. Okay, so you take the first variation and the second, well, this is the problem that you have. These P's are projections on eigenspaces, okay, for the Laplacian. What you see here is an observation that has been made by several decades ago, namely that the important thing here is that, so this B is the one here. I can play with two constants here. This is a conserved, all of these things are conserved. And I can choose, this is the Casimir, so I can choose the K, that I can choose so that the first variation is the equation that I want. And I have a freedom here with these parameters, but the first one comes from the rotation, so this is gone, so basically I have just one that I can allow myself to choose the way I want. And this is the expression of the second variation. Now I can choose B to make this have one sign, but here there is a problem. But the problem is not everywhere. So now here, what is clear here? Okay, so if f prime is bigger than 0, then this is positive. You can choose b equals 0 because that would kill, there should be a b here, that will kill this, okay? If f prime is between 0 and -6, these are the rigidity things that tell you these are rotated zonal solutions. This expression here is positive for all k greater equal 2. And you can handle the mode k equal 1 by choosing b equal -10. Okay? So there are some stability things that come out with this method. And Arnold. So basically what we have is that if any solution that will satisfy this will be stable in H2, and in particular the two solutions that I showed you, the ones that come from zonal by rotation for these special choices of F, both of them enter this framework, so they are stable. And now the next result that I want to talk about is this. So this is the critical level, if you want, where f prime could be -6, and you have eigenvalues, eigenfunctions corresponding to this second eigenvalue. And these are Rossby-Haurwitz solutions. So this, you cannot get to this by the Arnold method. And the question is, if you take zonal flows, okay, so this would be a zonal flow that will have the degree, the size of the eigenvalue tells you how many times there is only one zonal flow in the eigenspace, and that one will oscillate, and basically the number of oscillations is proportional to the j in the eigenvalue. Yeah? So this is the first Rossby-Haurwitz solution that doesn't enter into what we did with this Arnold method. And the evidence, the numerical evidence here is unclear. So some claim that it's stable, some claim that it's unstable. It is as a mathematician, it is very frustrating to talk to people in geophysics, because the overall viewpoint is that all the theory is clear, we understand theoretically everything. It's just what we need to do now is to work out the details. And basically, working out the details doesn't mean deriving model equations in a systematic way. It just means it's data-driven. So they look at data, and then they add some terms that statistically fit this data. So it's very hard to discuss. To ask questions never have a clear answer. Is it stable? Well, it depends. And everything depends on too many things. So in particular here there are, in this recent paper there are conflicting numerical simulations. Some indicate that it's stable, some indicate that it's unstable. At some point there should be unstable, because Jupiter and Saturn show that, but they wiggle a lot. So at some point you would have these things that would be unstable, in the sense that you expect these big vortices that come there and there are the red spot is not a good example because it doesn't seem to grow very much, but there are others that seem to grow. So if there are too many oscillations, it seems to be. So if there are few, then this Arnold method works, and this would be the borderline. And what we can show is that this is stable. And we worked very hard for this. So first of all, non-zonal of this form are unstable. And this is easy to show by using the invariances. So basically the proof is here. So the claim is the following. You take, this is a Rossby-Haurwitz wave, and it's a non-zonal one. There is a genuine dependence on phi. And to be this c, the speed has to be this for it to be a Rossby-Haurwitz wave. And it's unstable in the sense that you can find a sequence converging to the initial data in H2, and the supremum over positive times is bigger than epsilon. Okay? And this is easy to construct because you can estimate this in this way, and so this is easy to prove. The more complicated thing is to show that this particular one, so this is the Rossby-Haurwitz wave of index 2, that this one is stable. With beta is 0, this is the thing with Arnold method. This is now with beta different from 0. So, and this is a zonal flow. It's a zonal flow, but one that has more inflection points. And for those that work on this kind of stability thing, the inflection points are very bad if you try to do them with Arnold's method. Right, so what you can do is the following. So we take the string function, we develop in spherical harmonics. We have these coefficients. Now, because we talk about real valued functions, there are some, this is real valued, so the coefficient with minus m is minus 1 to the power m times the coefficient with m, complex conjugate. The ones with index 0 are, this is an integral of motion, and this the ones with plus minus 1 were integrals of motion multiplied with an exponential of absolute value 1, so the norms are the same. And so if you take into account conservation of energy and invariance of this, so this is one special Casimir, then you can make this expression small if initially this is small. And this is a 3 here, this is not a typo. Okay? The 3 comes because for greater or equal 3, this is positive. Okay? So what you learn when L is 1, this is... okay? So what you learn is that when L is 1, you don't need to look at this because that's taken care of these things. So basically, the interesting thing, and this was known for a long time, is that the instability can only be caused by an energy transfer between spherical harmonics of mode 2. So it's only the ones of mode 2 that can transfer energy to each other. This is how instability can be brought about because of this kind of formula in combination with this conservation laws. Right, so how do we deal with this? Well, we have many conservations. We have all these Casimirs. So basically here, any function I take of this, I will get an invariant. The problem is that, of course, this one is easy to compute, but what we do take this a power 2, 3, and 5. 4 doesn't bring you anything new. So this invariant will give you, so basically what the C's that you have all in this expansion, what this tells you is that when this L is 0 or 1, that is taken care of. When the L is greater or equal 3, that also stays closed. So you only need to look at the L equal 2. Okay? And when L equal 2, you have 5. So you have 5 coefficients that you need to show that if they are, that you can control them. They cannot. And the way to do this with 5, well, they are 5, but then when you think of it, there is also this relation. Sorry. Well, I think I wrote it here. Yes, it's here. So there are 5, but they are complex conjugate. Okay? So actually they are in absolute value, because this is the absolute value you want to control. In absolute value, they are 3. So you have to control 3 things, and this is why you take 3 polynomials. Now, it is, you write down what that means, and you get polynomial expression with these 3 coefficients, nonlinear ones, and you know that these 3 expressions will remain small because they correspond to this. And then it's an exercise, well, it's analysis, but it is, you have to show that if they were, that if they are closed at time 0, because of the special form that is, I'm not going to write them down because they are really horrible, and the coefficients are, because see, all these coefficients are, there are these things, these spherical harmonics, and the problem that we encountered here, in quantum mechanics, they use these spherical harmonics, but you always have to see what kind of inner product is, and so we actually had to do all the calculations by ourselves to make sure that we really have the right coefficients and everything. But so what I mean, these 3 things, if you write them down with 3 polynomial expressions, you can show that if they, you cannot solve, we don't know how to solve them explicitly, but we did see some structure and we showed that they stay closed, and this means that the zonal Rossby-Haurwitz wave of degree 2 is stable. And the others are unstable. So the question is, if there is, and now the conjecture, we are working on this at the moment, and what we somehow, what seems to be possibly the case is that, so if there is something else that it's stable, it's the next one with the 3. And there maybe this has to do with the fact how fast the planet is rotating. But at the moment this is just speculation. So here it doesn't matter what the rotation rate is. They will all be stable. So the third one, I think for linear stability would be spectral stability. It's not easy, but it's easier to do. And it's also kind of strange because it depends how well you do it, or also at the level of linear stability, the statements are not very clear. But if there is hope for stability, it would maybe the next one, depending. I mean, there is this folklore that if the planet is rotating faster, then things should be more stable. And then you ask, what is it? What is that thing that will be more stable? Well, flows in general, but then you want to know which one. Well, not very clear, but if it rotates, and the results that are available are things that rotate so fast that other than rotation you don't see anything. So what is available on the analytical side is not useful. But there is the idea that if the planet rotates fast, it should somehow keep things together. But this is almost the level of information that we were able to get, which is not very much. That's all what I wanted to say.
Thank you very much. Are there any questions?
How do you construct this sequence P0 and hat in the unstable case? So
here.
Yeah.
I take
yes. Sorry, I didn't find.
It wasn't.
Okay.
So you just. This is the typical thing. You add the 1 over n to the sign, and then you compute, right. and this is enough for it to.
In this direction.
You just that will change. Now the conjecture is, and there is a recent paper on arXiv that is 40 pages long, and I didn't. We made a remark here that, of course, they are unstable, but you hope that they will be orbitally stable.
Yeah.
So apparently there is a paper on arXiv where this result is claimed that they are orbitally stable. Because basically what we do, we alter the speed in the construction. So then, yeah.
Yes.
I have a couple of questions. So the first one was when you have your stability condition for the Arnold method.
Yes.
So it involves a kind of ratio.
Yes.
It reminded me of the Fjordhoff criterion for shear flows.
Yes, this Fjordhoff thing is actually this thing here. Sorry. So Fjordhoff is this thing here.
Ah, okay.
It's the thing that the transfer is only between mode 2.
Ah, okay.
Okay. So I mean, this is one reformulation of that thing.
Okay.
Because then, so this is a rigorous thing, and then you can do some linear. I think what he did, and he said, okay, this is transferred at level 2, and then let's do some linear analysis and draw some things. But the useful thing for us would be this identity that is due to him.
Okay. I had another. Is that okay?
Okay.
Other questions. So about the instability for Saturn and Jupiter, I didn't quite get. Do you expect it to be a kind of high frequency instability because of all the wiggling?
I don't know. The only thing I said is that I think, I mean, if you look at how, this is at some scale, yes, if you take a further scale, then it will, I mean, this, somehow the logic is that if it does too many things like this, it would be unstable. So I don't have any conjecture what kind of instability, but this pattern, if you ask anyone in geophysics, it will not be stable because it's oscillating too much. And the same for Saturn.
Okay,
but this is heuristics.
Okay. And about the rotational stability, okay, the way that I understand it for geophysical flows, but 3D flows, is that the rotation forces you somehow to be 2D.
Yes.
And that's the reason why it's more stable because.
But here we are already 2D.
Exactly.
So that
2D,
we are already 2D because we are in the stratosphere.
yeah.
So that we cannot, that will not be a bonus here. But still, I mean, somehow, maybe you can hope if omega, I mean, if you ignore nonlinear things, I mean, the papers that I've seen are half rigorous, and basically, if omega is big, if the rotation is fast, you throw away everything nonlinear, and then it will be okay. But it's a very simple calculation obtained at the expense of throwing everything away that you don't know.
But do you see a kind of, I don't know, spectral gap? Do you see how it moves the eigenvalues?
Well, what I've seen is very rudimentary, so, and it's at the linear level. This is, I mean, it's something where I just take it on face value that somehow the size of the rotation should play somewhere a role, but I wouldn't be able to say where.
Okay.
So these pictures of Jupiter and Saturn that geophysicists conjecture are unstable. What is the time scale under which you would see instability? Like, would you see the instability within our lifetime? Is it that
Oh yes, there are things that. So, I mean, the problem is that it seems hard to believe, but for example, it's not very clear what is at the core of Jupiter. So there are very few things that are known. When we talk about stability, we only talk about a few hundred kilometers from what we see here. So it's this, and what you do see here is that, I mean, it seems that there are kind of vortices that get created, and in a few years, they grow and then they die. So, but they really grow a lot. On the other hand, there is the red spot that, well, kind of moves a little bit, but has a, I mean, on visual inspection would look like something stable, but that's a different thing. So here, what they do observe, it's measurements by satellite, okay? And they did observe some small perturbations on both things that grew and then they disappeared. So there are things that are on scales of a decade, I would say, which is long but not very long.
Okay, then let's thank Adrian once more.